And now we're going to go to a focus demo by Mario Juric on the science platform. So I think, Mario, I'll give you the floor.
Thank you. And it's always good to be on ADAS, even if virtually, even if at 11:30 p.m. local time. I'm Mario Juric. I'm from the University of Washington Juric Institute, and I'll tell you something about the checkpoint restore and live migration for science platforms, and I'm actually going to demonstrate what we did there as a prototype. So to quickly just introduce where I come from, I'm the director of Juric, which is a center built to advance and support research with complex or large astronomical data sets, and LSST in particular. We have a very strong software group in Juric, more than about a dozen people, total of about 25 people in total that are working on various technologies related to astronomical software. One of the things that Matthew mentioned, the streams for ZTF and LSST and the introduction of Avro and Kafka as a transport layer were pioneered here with Maria Patterson and Eric Bellum specifically. But what I'm going to focus on today is our science platform research, and specifically the one aspect of making them a bit more efficient. So to motivate this a little bit, let me talk about the present day archive architecture. So this is typically how users interact with archives. Archives are these places where there are large data sets in the back end. User is out here and they access through a front end some subset of that data set. They access the subset, they download it, they run analysis on a local analysis resource, repeat that over and over again until they converge to what they care about scientifically. And we all know the issue with this, and the issue is this this paradigm breaks for large data sets. ZTF is already making it more difficult. LSST will definitely make it more difficult. Even 0.1% of LSST is still an order of a terabyte. The solution's been known for a while now. It's bring the code to the data rather than bring the data back to the code. Which leads us to take this archive architecture that we have today, and it's likely going to morph into something that looks more like this. So what we have now, rather than a fairly simple front end that's designed to enable downloading of the data, we have rich web front ends, both portals and rich notebook type platforms, and the analysis resources now incorporated into the archive itself. Now, this is how most science platforms today are being envisioned. There's a slightly different way to build this. Rather than actually physically build the computing resource together with the archive, what one could do is utilize the cloud-based resources and simply shift all the data sets into the cloud. In that case, you could run the science platforms on the cloud as well. And there's a number of interesting things that become possible that way. For example, science platforms from one institution could access all the data sets that are available in Science Cloud at quite high speed. So you effectively get something like Science Platform from ESA potentially being able to access LSST data set or vice versa and so on. This has some interesting possibilities and opens up a way to build a whole different ecosystem of science platforms and ways to collaborate, but it is a slightly different talk. What I want to focus on here is that for all of these concepts, Jupyter is almost always the default science platform user interface. And the reason for this is that our users, the astronomers, are very used to this, this tool set, and that it's natively built to work over the web. So the bit that I said about our users being very used to this tool set is important here because they developed a lot of expectations from years of use of Jupyter on their laptops and on their servers in their home institutions, on their desktops. They've developed some expectations on how that is supposed to look like and how one is supposed to interact with Jupyter. So what do Jupyter users expect? And this comes from 3 years of running Jupyter instances for hundreds of users, whether it's schools, educational, or whether it's locally for research. What they expect is, first of all, that their notebooks are long-lived. They expect to go to lunch or take a weekend off without closing their notebooks and interrupting their work. They also expect to have access to all their files and scripts from their notebooks because they typically run them on their laptops or on their desktops. They expect to be able to utilize almost all available memory. If they run over, what they expect to happen is that failure is soft. So that typically, what typically happens in our institution is you run, you exhaust all the available RAM. You suddenly see a slowdown because the computer starts swapping, or you get a Python level out of memory exception. The whole system doesn't crash. That's the important message here. They expect to be able to utilize as much CPU as they can get, and they prefer not to compete for CPU and memory with other users. That's why still all of our researchers really like to have their own laptops and work on their laptops. Now, in the science platforms as we currently have them, what are users typically given? The typical implementations that everybody runs, and including ourselves for ZTF research, is JupyterHub and Kubernetes. There are two ways to split apart users and to launch JupyterHub instances. One is you could oversubscribe a large machine and therefore conserve resources, but then each user has a very small slice of CPU or memory in that large machine. Or you could go in the other direction, allocate one host per user, one virtual machine per user. And that's really nice from the point of view of the user. It gives them isolation, predictability, but it also gives increased cost to the operator. There are issues with how JupyterHub runs in Kubernetes. By default, it'll terminate if inactive for a preset period of time, by default about an hour. And that's unpleasant for a user who's used to working on their laptops and for the notebooks to run all the time. The other issue is that in case of, if the user runs out of memory, the result is hard termination. So the entire Jupyter kernel just dies. And that is because Kubernetes tries to defend against the case where one container goes over its limits. And then another issue is that if the resources are insufficient, the user must manually move to a new VM. Let's say you've assigned a 4 GB or 32 GB RAM VM. The user is doing some data analysis and realizes, oh, I need 128. Now they need to shut it down, start it on a different VM, and then rerun their notebook at that point. So the platform operator's choice here is generally either poor resource utilization or poor user experience for the user. And our experience has been the users essentially will not use a platform with poor user experience unless it's the only way to do the work. So they will fight tooth and nail not to do it as long as there's a different option. So I think there's a good reason to look into this. How do users actually use Jupyter? So everybody wants their notebooks to run 24/7, but we've actually done a study and looked at utilization patterns. And most of the time, notebooks are idle. Average research work utilization is only 10 to 20%, depending on the user and depending on exactly the type of event or work. So that's about 3 to 7 hours per day. And that kind of makes sense. And it's minimal over the weekends. Very few people actively run a lot of things over the weekends. So there's lots of room for resource management. What we need to do here is to provide an illusion to the user of a constantly running notebook. We need the ability to checkpoint it to a disk while it's not being used and restore it back to the same state when the user is back. And that is something that we realized that we probably can do and went on to implement a prototype that I'm going to demo now. So this prototype is known, is called ELSA. It freezes Jupyter servers and then freezes them back again. Those of you who have daughters that are of young age might probably know where the reference is coming from. And let me show you how it actually works in practice. So here, this is in the browser. I have a live instance of ELSA running. And it's just a plain old, looks like plain old JupyterHub. I'm going to sign in with my GitHub ID. And the first thing that I'm offered is, which server do you want? And here we just configured 3 servers to make things simple. A small one with 1 gig of RAM, there's a medium with 2 gigs, and large with 4. Let me begin on the standard one. So what happens now is I'm going to get my Jupyter started. Nothing out of the ordinary right now. I have to wait a little bit because it's pulling the container with the whole notebook. And here we go. So The next thing I'm going to do, I'll start this this notebook that we prepared for the checkpoint restore demo. So what I want to show here is that I can freeze this notebook and unfreeze it as if nothing happened. So I'm going to do two things. This is intentionally a very simple notebook. I'll create a variable that contains the world's hello world. And then to show something a little bit more complex is I have a file here that's called test file that has this contents. These are individual lines. This is a test file. It shows that open files are checkpointed correctly. And what I'm going to do is I'm going to open this file in Python, and I'm going to read a couple of lines. So here's this is a test, and I'll pause here. So now what I'm going to do is I'll hit this button here. Oops, I actually have to save it. I'll hit this button, and what that's going to do is it's going to take the contents of the memory and everything that's changed in my Jupyter server and store it to disk and shut down my Jupyter server. And that usually takes about 20 minutes or so. And we actually know how to speed it up significantly, just haven't gotten to it yet. And here we go. At this point, my server is down. I kind of stopped it halfway through that notebook. What I'm going to do next is I'll start it back up. So this looks the same like before. I'm going to pick standard again, and I'm going to run start. But now what's going to happen is rather than that the server being started from scratch, see this message? It's going to be restored. And if you look at this notebook, note that it's green. It means it's running. So if I go here, and now I can go and print the value of this variable. Note that this is input 8, and it's still hello world. And let me read a few more lines from the file. Here we go. We stopped at test and continue that file, just as you would expect. Let me try it again. Now it's white space, and then it shows, et cetera, et cetera. So what I showed you just here is that we've developed the ability to take a running notebook, store its state to disk, and then restore it on the same machine. This is already great because it makes it possible for users to, or operators to store inactive users' notebooks on disk and then restore them when users are back without loss of work in those notebooks. But we can do better than that. This button here is a shorthand for migrate. What I can do is I can take this notebook and then checkpoint it, and rather than restoring it on the same machine, I can send it to a larger machine. So note here, this tells me that I have 800 megabytes of RAM available in this VM. Now I'm going to send this notebook to my medium server. So again, this goes to checkpoint process. It takes about 20 seconds or so. And then after checkpoint is done, because I hit migrate, it's going to immediately start this server on, start this notebook on a different server. And here we go, now it's running, now it's starting it up on a different server. And when it comes back, okay, let me go to my notebook. One thing to note this is now 1.8 gigs that they're running here. My hello world is still there. I stopped at shows. Let me read a few more. That open files are checkpointed correctly. I could continue this demo a bit more. I can now move this, this notebook back to the smaller machine because I'm still using less RAM than that machine has. And you can now start imagining all kinds of resource management things you can do with this capability. That all works. So I'm not going to do that in the interest of time. I'm just going to stop it. Now, let me go. Oh, here we are. One thing you may ask is, well, you basically didn't run anything here. Will this really work with a more complex piece of software? And to show you that it will, what we did was we loaded up all of LSST's 2 or 3 million lines of code of the LSST stack into this system. And here's a notebook that depends on LSST code. This is actually a demo of the LSST blender. And so what I can do is let me start this. So this bit here imports all of the LSST AFW and image and detection. And these are quite sizable pieces of code with both C++ and Python, C, external libraries, etc. And so what I'm going to do here is this element here actually reads a data repository, an LSST data repository, which is an internal database. So this opens a SQLite database to find out where the files are in the system. And I'm going to run this kind of halfway through. This may take about a minute or so. Let me get to this point. So it will take about 30 seconds for it to get 30 seconds to a minute to get this point. What's happening right now is this code is loading a number of images, and you can tell that the memory is getting uncomfortably, memory limit is getting uncomfortably high. It's loading a number of images, and it's going to, once it gets to this point, it's going to show us RGB coads of the images it loaded from this data set, from this repository. And so I think this is going to take a matter of 30 seconds or so. Here we go. And here's a nice image. This is a fairly complex piece of code. This is 10 years of development is in this code. And what I'm going to do now is I'll checkpoint this. I'll basically migrate this notebook to my large instance. So I'll hit migrate and go to large. Now, one thing you're going to notice here is that this migration will take longer. It'll take about a minute. It'll take probably a little bit more than a minute. And the reason for this is quite amusing, let's say. The actual checkpointing of this process takes something like 4 seconds. The rest of the time is spent in gzipping the output files, because by default, the software we're using for checkpointing, I'll talk about it in just a second, wants to really gzip all the checkpoint files, and there's no way to turn that off. This is a very trivial fix that we're going to make and submit upstream to be able to avoid zipping. And that will, in essence, turn this from a 1-minute operation to something that's closer to a couple of seconds. And here we go. And so now it's restoring on a larger machine. And it's almost there. The restore, as you can imagine, also takes slightly longer because now it has to unzip this this file, and this is all running on a fairly small server for this demo. But here we are. I'm going to go to my notebook. Let's see, where did I leave off? Here. I'll just run this cell. This is now building another RGB code, and here it is. So this shows that, and note that the available memory has changed. So this shows that I can actually move a quite complex piece of code from one machine to another. So I'll stop with my demo here and go back to the slides. What is it that our present system can do? It's multi-user, it's fully scalable, so it'll grab new machines as needed as there are more users. JupyterHub deployment. Each user is allocated their own VM. VMs have swap, which allows them to degrade rather than fail when memory is exhausted. And you get out-of-memory conditions at a Python level. As a Python level failure, you don't get the whole kernel crashing if you run out of memory, which is what you often see in Kubernetes deployments. User notebooks can be checkpointed and VMs deallocated, shut down. So that means there's no spend, no money being spent while they're checkpointed. And when users restore them, it reestablishes all state. And there's a little bit asterisk to that, and I'll tell you about it in the next slide. This gives the user the appearance of an always running host. It's quite useful. VMs can be migrated to different VM instance type, or I should say Jupyter notebooks can be migrated to different VM instance type. And you can go both ways. You can upscale and downscale. The software sees new CPU and RAM without restart. That is really cool. You can start some analysis, realize you don't have enough memory, move over to a larger memory host, finish it without having to restart your notebook. Sometimes you build notebooks that take half a day to get to the point where you are at, and you really don't want to restart them, and this enables you to do it. And checkpoint restore times are sort of reasonable, but they grow proportionally with RAM size, and we know how to fix this. This is one of the first things we want to fix in the next couple of weeks. Limitations. Right now, there's no preservation of open TCP connections. So if you have a TCP connection that's open to the outside, that will get broken. Now, the good thing is we actually know how to fix this. The software that we're using underneath has the ability to migrate TCP connections as well, and that's one of the first things to do. We cannot checkpoint some unusual APIs in corner cases, which typically don't appear in scientific software. Just for laughs, we tried to dump a full-blown desktop VNC session that we were running within Jupyter, and that didn't work because it was complaining about iNotify. HPC libraries with special hardware support and InfiniBand libraries and so forth may not, it's not clear how they're going to work. Again, it's not clear that we need them in this context. And the thing that we do definitely need is support for GPUs and accelerators. Right now, there's none. So if you're using a GPU, you cannot checkpoint. But this is something that's being worked on. The important bit here is that failure to checkpoint is non-destructive. If the system isn't able to checkpoint a notebook, it can just give you a message and say, I cannot checkpoint, please continue working on it as is. So you're not risking your work by trying to checkpoint. And that's a really nice feature. All right, given this is ADAS, this is the fun part. Let's talk about technology. Let's see what's under the hood and how this works. This is the high-level architecture what we have right now. So the deployment that I just showed you runs on DigitalOcean, which is a cloud provider that's just really convenient for development. We chose it for simplicity. We can run this. We can move this to AWS, GCP, or Azure relatively easily. It's standard JupyterHub notebook containers and both for the hub and the notebook. And a fairly standard setup. They're running directly on VMs, and we've written our own lightweight orchestration layer. The reason why we couldn't use Kubernetes is because it has no support for checkpointing and no swap. But in the long run, we'd really like to integrate this with Kubernetes. We use Podman as the runtime engine, as the container engine rather than Docker. I'll tell you about that in a second. And for checkpointing, we use something called CRU, which is the most interesting bit, I think, the most important bit in this story. What CRU stands for is checkpoint restore in user space. It can freeze a running container or individual application and checkpoint a disk. It started in 2011 by OpenVZ developers, and it was merged into the mainline kernel in 2013, late 2013. So it's been there for a while. And the main insight that they had was that the Linux kernel already supports numerous interfaces for freezing, inspecting, and changing the state of a process. So that means that you can probably dump it from user space. And that's what they did. There was a lot of skepticism early on. This is a famous / infamous post by Andrew Morton, one of the kernel developers, that this is a project by mad Russians to perform checkpoint restore, et cetera, which is why I love this thing, because it's kind of a triumph of the mad Russian here. It actually worked in the end. It supports checkpointing of virtually everything that we need to checkpoint containers. And the performance is such, other than the gzip issue that I mentioned, that snapshotting and restore can happen in 1 to 2 seconds. And this is really disk read and disk write bound. So I don't know what the actual limit is. And there's a mode called lazy migration mode where you can actually migrate in tens of milliseconds. We haven't actually tried it out. The file system has not changed between invocations. That's one limitation. And the file system must be the same at the inode level. And this is where containers come in, because containers allow you to keep that integrity. For you, is difficult.
Mario, maybe a few minutes left. So
yeah.
I don't know if you want to take questions. I mean, there is at least one.
I have maybe 2 more minutes, and then I'll take questions.
Okay.
So the bit that's really important that made it this easy to use is Podman, which is Red Hat's implementation of Docker. Basically, with these 2 commands, you can now checkpoint the container and restore it. And then the thing that we spend most of our time on is integration with JupyterHub. Now I'm going to skip most of this in the interest of time, but There are a couple of levels. We had to implement orchestration that works without Kubernetes because we cannot use Kubernetes because it doesn't support it yet. We've implemented it using JupyterHub spawners, and it's a quite elegant implementation, only about 400 lines of code. The user data storage has to be on a shared file system, so on a network file system. That solves the problem of how do all these different machines see the same file system when you actually move processes from one to the other. The backend integration is such that we've overridden the start and stop points in Jupyter to mean checkpoint and restore, or restore and checkpoint. This is not ideal, and we should really modify Jupyter upstream to have true checkpoint and restore, but it works for now. And finally, we built a user interface that you've seen. So why is this useful? Because now, if you're running a shared server, you can opportunistically checkpoint inactive processes. And let's use a snapshot from our group server, and there are many of them and take up a lot of memory. If you're running on-premise SaaS platforms, you can give significantly better user interface because you don't have to terminate users. You can just checkpoint them. But if you're running in the cloud, this is where this becomes extremely useful. So we've looked at how what the duty cycle of typical notebook is. It's about 15%. And this, combined with running on spot instances, which you can now do, can bring your cost down by more than factors of 10. So here's an example with an M5 instance. And if you think that you can work with a T3 instance, it gets even better. So we're talking about potential factors of 10 here. So this becomes comparable and sometimes better to than on-prem total cost of ownership. So to finish this, looking ahead, these are the things that are going to land in the next couple of weeks to months. Speed up, speed up, speed ups. That's the most important bit. We'll do some generalization, migration of network connections. Sub-second line migration is on the horizon, and Kubernetes integration is one thing that we would really like to do. And there's a ticket that started that. If you want to test drive this, let us know. Go to this repository and open an issue. And we're really looking forward to collaborations. We at Dirac, we develop software. We don't tend to run it other than for ourselves. And we'd love some collaborations here with platform operators and software enthusiasts to go and build this further. So thank you, and love to take any questions if there's any. And if you like work like this, join us. Here's a link to a couple of job ads we have out. Thank you.
Thanks a lot, Mario. So I think there is one question from James Docknell. How are ABI issues handled?
ABI issues? Can you be more specific?
Okay, then
I don't see ABI issues here.
Okay, well, I don't know. I can't. Or maybe let's do the following. Can I suggest, if James is online, that maybe he can ask the question directly to Mario through Discord. Then you can be more specific. So because it's it's time to move to the buff. So okay. So thanks a lot, Mario.